Good afternoon, everyone. We now move on to our second lecture of the day. I may now request our second speaker, Professor Shan Chakravarti, to take over and deliver his lecture on GR. So, please.
Okay, thanks, Saraswati. So let me start from where we left yesterday. If you remember, I introduced just the two different types of four vectors. I did not define what these two different types, contra and covariant, are. That we are going to define today, or try to explain in terms of physical quantities, which type of vectors should we call the contravariant vectors, which type of quantities we should call covariant, all these things. And then I gave you a prescription that given a covariant quantity, how can I raise or raise the index, or given a contravariant quantity, how can I lower or make a covariant object out of it. And in both the cases, when we are in the regime of special theory of relativity, we used the metric, the Minkowski metric, eta mu nu. This was our convention, -1, +1, +1, and +1, the metric diagonal element. So this metric is being used to raise and lower the indices. Now, I also gave you some hint of how to define the squared length of a vector. This is the way that we generally utilize the definition of inner product in case of for vector, that if I have a quantity which is contravariant with superscript mu, and I have another quantity which is having some subscript mu, so one contravariant, another covariant object, then I can write this thing as eta mu nu, both contravariant objects, a mu a nu, or eta upper mu nu, which is the inverse of this eta lower mu nu, times a mu a nu, which are the covariant objects. So explicitly, if you want to write, what does this mean? If you remember, yesterday I told you that if I have two objects which are repeated, two indices which are repeated, then that repeated indices means that there is a summation which is explicitly written in this particular step. And then I have broken it down because mu is repeated. So I wrote it as a0, a0, a1, a1 in this manner. And because of our convention that the first term, the time component, is -1, so there will be a -1 if I raise this index of a lower 0 or covariant a0 to upper a0. That means contravariant with the metric eta 0, 0. So eta 0, 0 is -1. So this first term will gather a negative sign in front of it, and then it will be a0 square and the 3 vector a squared. And also based on the squared norm, this is not a 3-dimensional vector. There is one sign which is negative. So this clearly tells us that if this object is more compared to this object, then this a0 square minus sign with a minus sign will dominate, and this whole quantity may become negative. So in our convention of this particular choice of the metric, we will call this object that mu negative, then we will call mu to be a time-like vector. If this is 0, then we will call mu to be a null vector, and if this is positive, then we will call it as a space-like vector. Now, recall that we defined the Lorentz transformation in this manner. So let me go back. So this is the manner in which we defined the Lorentz transformation, which related x with x prime, t with t prime. The two very important features of this transformation are the following. That first one is that it mixes space and time. That is the first very important feature. And the second one is that it has the linear dependence. Even though it mixes space and time, the linear dependence of x and t. So x prime and x are linear in x and t. T prime and t, they are also, this also is linear in x and t. So these are two very, very important and interesting observations when we try to generalize this approach of special relativity to GR. But for the time being, just keep in mind that the relation between x and x prime and t prime, they are linear in x and t. So this equation is the one that we have introduced in yesterday's class. So the primed coordinate and the unprimed coordinate, they are related by this L mu prime nu. And how this L mu prime nu actually tells us, because it is this L mu prime nu is a 4 cross 4 matrix, and this 4 cross 4 matrix, we will have some non-zero quantities, and these non-zero quantities will be gamma v and gamma vt. If you may go back here, if you remember, this is what we have seen in yesterday's class. So this L mu prime nu is an object, is a matrix with some non-zero elements in it, and this is the matrix that is being used to relate the x mu prime with x mu. That means it relates the primed coordinates with unprimed coordinates. Similarly, we can say that the inverse transformation also exists. That means I can write x mu in terms of the primed coordinate x nu prime, and in that case we will have another 4 cross 4 matrix. This 4 cross 4 matrix M mu nu prime will be the inverse of the other matrix, which is L mu prime nu. And this is written mathematically as L mu prime nu M alpha nu is equal to delta alpha nu, where delta alpha nu is the Kronecker delta. Okay. So therefore, you can now relate, knowing this, you can now relate two primed vectors dot products in this manner. So A mu prime, I know how it transforms. It transforms with the help of this matrix L mu prime nu A nu. And I know the other vector B mu prime, and this B mu prime under Lorentz transformation, it transforms as M mu nu prime X nu prime. So B mu prime, I am writing it as M alpha mu prime. Now here is a word of caution in terms of using the different indices. See, both these cases, A mu prime and B mu prime, they are actually having the same index. Now what I am doing is that I am writing this A mu prime as, I am writing this as L mu prime nu A nu, and I am writing this B mu prime, lower mu prime, as M alpha mu prime B alpha. Now I have not used the same index mu while I have written this B mu prime. I have written a different index alpha here. So this is very crucial, because in principle this is a dummy index, because there is a summation. Anytime there is a summation over indices, they are called dummy indices. And dummy indices are something which we can always play with. Okay, dummy indices are basically repeatedly summed over indices, repeated indices. And this is what we have done. We have kept it as much as general possible. So this is alpha and this is nu, and then we are going to utilize the inverse criteria between these two matrices. Okay, so that is why we have written it here. It means that we have a Kronecker delta sitting here, and finally once I use the condition of Kronecker delta, that it is non-zero, it is equal to 1 only if alpha equal to nu, then I will replace this alpha with nu. So do not get worried or do not get scared with seeing these indices, because in GR we are going to use a lot of them. But if you try to sit with this and just do the calculations by hand at least once, I think it will be clear to you how to use the indices. Now, so the dot product, it shows that the dot product of between two four vectors, it is very important. This is two four vectors dot product is invariant under a Lorentz transformation. This is what this shows. Okay. Now I want to introduce the idea of tensors. Tensors are some objects which we are going to very frequently use in general relativity simply because they obey they transform properly under general coordinate transformation. I will define what this term general coordinate transformation means. It means that in the Lorentz transformation, remember I just now told you that in the Lorentz transformation, we have a linear dependence between x and t. So x prime is related to x and t linearly, t prime is related to x and t linearly. So these two relations are not the most general relations between primed and unprimed coordinate. I can always go to some coordinate which is not linearly related to the old coordinate. And in those cases, this whole idea of Lorentz transformation will fail. And this whole idea of introducing tensors will also fail in special relativity. So this is a very restricted set of discussion on tensors. We will generalize it today to when we discuss the mathematics relevant for GR. Now, because we do not have time to go into the detailed discussion of differential geometry, let me just introduce tensors just by saying that it transforms like a product of between two four vectors. For example, I have a mu and I have b nu, two different indices mu and nu. So I will call this product as a separate object with two indices, and I will call this a second rank tensor. Okay, this is a very, very bad definition, but this is some definition with which we can actually proceed. We will see when we need to generalize this more. Now, the next question is, if we go from one inertial reference frame or IFR, inertial frame of reference, to other, how does this C mu nu transform under Lorentz transformation? I have seen how the four vector transform, but now my question is how these two indices object will transform. So similarly, exactly in the same manner, I will write this C in the prime frame, mu prime and nu prime. And since I know that for this, I need to write this as C mu prime, nu prime, I have to write it as A mu prime, B nu prime. Now, individually, I know how these two objects, A mu prime and B nu prime, how these two objects behave. So I will write A mu prime as L mu prime alpha A alpha, and I will write this B nu prime as L nu prime beta B beta. Okay, so this is something which is all known to us. So that means essentially I have A alpha B beta, but A alpha B beta, it is nothing but C alpha beta. So I will write my final expression as L mu prime alpha, L nu prime beta, C alpha beta. So the index correction, I will term this as index correction, mu prime and nu prime. If there are two indices to be corrected, there will be two such matrices in front of this unprimed C alpha beta. That is the general rule. And this C alpha beta is generally defined as a rank 2 tensor, and it is a set of 4 cross 4, that is 16 quantities, which transform like the product of A mu B nu of two different four vectors under a Lorentz transformation. Okay. Now, since we have defined two types of components, upper and lower, but I have still not told you what actually physically do they mean. I will come to that later. Since we have defined two types of components of four vectors, we have two second rank tensors, which may be where I have two indices in the upstairs, that is contravariant indices, one index up, one index down. Another may be both indices down, both covariant. This is called a mixed tensor. This is a contravariant tensor. This is a covariant tensor. Okay, so these ideas generalize to tensors with any arbitrary number of components, contra and covariant indices. Okay, so that is essentially what I wanted to tell you, and exactly the same manner that you have utilized to raise and lower indices, that also goes through. You use the metric, Minkowski metric, to raise and lower the indices. Okay, that is what this statement tells. Now, multiplying two tensors produces another tensor with a different rank. For example, I have S mu nu alpha beta. I can always write it in terms of two different tensors. One is K mu nu and another one is U alpha beta. Now this K mu nu with one index up, another index down, this is a mixed tensor, and U alpha beta, which is a covariant tensor. Now what happens if I have one of the indices which is repeated? See, I have mu here, S mu, nu mu beta. Instead of alpha, I have replaced this index by the same mu which is in the contravariant position. So in the covariant position, I have a same index as the contravariant position. So I may write it as K mu nu, and I may write it as U mu beta. But this doesn't make any sense because this is a repeated index. I will write it. This means that the mu is, this mu index is summed over. So one pair of index will vanish and it produces a tensor with a lower rank. So if I have a tensor where two indices are repeated in like this, then we call that a contraction between the two indices, and the contracted index is also called a dummy index. Okay. Now, this is something which are some general properties that I had discussed in this page, but I will leave this discussion for the tutorial that Bhaswati will take today. This is some general properties of tensors which obey the Lorentz transformation properties. Rather, I will now go to a very general discussion on contra and covariant vectors, four vectors, because I find that to me, this is one of the most fundamental concepts in differential geometry and GR, but unfortunately, it is very often taught in a way that obscures the basic underlying physics. Okay, so I want to give spend some time on this concept. So I will first define or remind you what a contravariant four vector was and what a covariant four vector was. So this A with upper subscript nu was a contravariant vector. I used the Minkowski metric eta mu nu, or the flat space time metric eta mu nu, to lower the index and to get a covariant vector. The most important physical context in which a covariant vector, four vector arises naturally is that, suppose you may recall that A mu, how did we introduce the idea of a four vector? It was defined in analogy with the transformation of dx mu. Remember yesterday's class, we have used this analogy that dx mu, the infinitesimal element dx mu, it actually transforms with the help of L mu prime nu. This matrix we also defined. This is the Lorentz transformation matrix. And accordingly, I said any vector with one upper index, if it transforms in this manner, that A mu prime equal to L mu prime nu A nu, will be called a contravariant four vector. Now we just recall that here it is defined with the help of how a differential element dx mu prime transforms. We can also define quantities with subscript such as A with lower mu in terms of the derivative operator, which is defined as del x mu. Here the contra quantities are defined with the respect to this dx mu. There may be another set of four vectors which we can define with respect to the derivative operator del x mu, which is sometimes mathematically called dual to this dx mu. Okay, again, we cannot go into the mathematical details in terms of differential geometry. This is sometimes called dual to dx mu, del x mu being dual to dx mu. To define the corresponding four-dimensional object, we note that the differential of a scalar quantity. How do we define the differential of a scalar quantity? Suppose I have that gravitational potential phi, which is a scalar quantity. And now I can define the differential exactly in the similar manner which we have used in 3 dimensions, that if I have phi to be function of x, y, and z, then I will write it as del phi del x dx plus del phi del y dy plus del phi del z dz. Now here in 4-vector notation, in 4 space-time dimension, I write it exactly in the similar manner, del phi del x mu dx mu. Since mu is summed over, this means that I have all the 4 terms in this summation. But you note this expression very carefully. Doesn't it look like a dot product between dx mu and del phi del x mu? Exactly, it's exactly looks like a dot product between del phi del x mu and dx mu. So this transform as a covariant 4-vector under Lorentz transformation. This object, therefore, you can say, because if you remember that if I have a contravariant 4-vector and a covariant 4-vector, this is a scalar, and this scalar transforms exactly in a similar manner under Lorentz transformation. So this object transforms as a covariant 4-vector under Lorentz transformation. So remember that the components of the 4 gradient, you all are familiar with the 3 gradient, right? So this gradient operator you all know. So this is I cap del del x. I am writing in a specific coordinate choice, which is Cartesian coordinate. This is what you are familiar with. Now if I want to generalize this in 4 dimension, the 4 gradient of a scalar are given by the covariant components of a 4-vector. For example, I write it as v mu, which is del phi del x mu. Now x mu, the 0th component is ct, so I have 1 by c del del t of phi, and then the rest component will be just the spatial component del del x, del del y, and del del z, which is nothing but gradient of phi. Okay, so this is how we denote them. This is how we denote the quantity. This is the del with a lower of mu phi. Okay, so this is direct generalization of the ordinary 3-dimensional gradient operator. Look at it more closely. I just mentioned that this object is a scalar, but what is a scalar? Scalar is something that phi prime x prime is equal to phi x. That means at a given point, it has a value. When you do a Lorentz transformation, that value does not change. Think of the temperature gradient in the room that you are sitting. If in a room there are 5 people, everyone is exhaling and inhaling, the temperature near the people, the persons who are inside the room will be little bit higher. And then as you go towards the roof, the temperature will basically start to reduce. So that will give you a temperature gradient in the room. Temperature is a scalar quantity. The temperature gradient essentially will transform as a covariant vector. Okay, so then you ask this question, how does this quantity del phi del x mu transform? So you anytime anyone asks you that how such a quantity transforms, then you will immediately take the prime and write the transformation rule. For example, here del phi del x mu, I want to see how it transforms. It will be written as del phi prime del x mu prime. Okay, so this is del del x mu prime, del x mu, and then I will use a chain rule, and this is del phi. This object del x mu del x prime mu, this object is nothing but our good old friend m nu mu prime. So you can clearly see that this m nu mu prime, which is the inverse matrix for the Lorentz transformation, is sitting in front of del phi del x nu. So this object definitely behaves like a 4-vector under Lorentz transformation, but not with the metric L, but with a metric M. Okay, matrix M. Okay, so m nu mu prime is basically the inverse of L mu prime nu. This relation, remember, it holds. Okay, so d phi, which is defined as del phi del x mu dx mu, is an expression of dot product between del phi del x mu and dx mu, and this object transforms as a covariant 4-vector. Okay, so roughly speaking, The contravariant vectors are those, they are representing the tangent to the path, for example, position vector, velocity vector, etc. Covariant vectors, they represent a change across a distance. That means they are basically representing some slope or gradient. Okay, so for example, gradient, normal vector to a surface, these are the examples of covariant vectors. And of course, mathematically, there is definitely a change in the transformation property. Here, this object, the contravariant component of a vector, they transform with this transformation matrices, and the covariant object transform with a different set of objects in front of the transformed quantity. However, these two objects, they are related. This is our good old friend L mu prime nu, and this object is our good old friend M nu mu prime. So in special theory of relativity, this L mu prime nu, remember I told you many times that this L mu prime nu is an object where I do not have any x or t dependence, because this is the derivative with respect to t and x, and the Lorentz transformation being linear in x prime and t prime, or x and t, when I take the derivative, this object becomes a constant. Okay, so this consists of gamma, or this can consist of the constant velocity v. So this basically the coefficients are constants. So therefore, the way these two coordinate transformations are related is just a linear relation. It's just a constant multiplying this object. Okay. Now, to be more more physical, let me add another page here. I wanted to go a little bit more further into this discussion. So basically, if I may recall, if you may recall that for contravariant vectors, if I write v mu prime as del x mu prime del x nu v nu, it transforms like a coordinate differential. That is the first thing that you should remember. Coordinate differential. The second important point is that a contravariant vector basically tells you how to move in space-time. Okay, so it represents an actual direction. Okay, for example, you can think of position vector, you can think of velocity vector. Position vector, infinitesimal displacement vector, velocity vector, momentum vector, everything is an example. For example, you can define u mu as dx mu d tau. You can define the for momentum as m u mu. These are all examples of contravariant vectors. Okay. Electric current is another example of such thing. Now, why do we call these quantities as contravariant? Suppose we just stretch the coordinates. For example, I am in a primed frame, and the primed frame and the unprimed frame, they are related by this relation. Remember, Lorentz transformation will always give me a relation which is constant in front of it. So that means one unit in this new coordinate, primed coordinate, corresponds to 2 units in the old coordinate. However, a displacement of 1 meter should still represent 1 meter physically. That means dx prime equal to 2 times dx. The components must compensate accordingly, and therefore the transformation law that we have mentioned holds, and this is why they are called contravariant vectors. Now, covariant vectors, on the other hand, has a different philosophy. It is a completely different object. As you may remember, a mu prime, it is del x nu del x prime mu and I will have nu here. A covariant vector or covector, it does not point somewhere. It basically does not point in any direction. What does it do then? It measures the vector. Very crucial, it measures the vector. Think of it as a machine that takes a vector and produces a number. So that means you think of it as this. It is a machine where you give a vector as your input and it gives you a number like this. Okay. So this is a scalar. The final number that you get is a scalar. So what is the physical picture? You imagine some contour lines. For example, you imagine some contour lines of temperature. So these are isotherms. Okay. The gradient points perpendicular to the contour. All of you are familiar with that, right? So it does not represent any kind of motion. Instead, it tells you how rapidly the temperature changes if you move in a specific direction. Okay. So that means it kind of gulps down a displacement vector, which is say dx mu. It eats a displacement vector and displacement vector, and it gives you a or returns you a scalar. Okay. So what are the examples of such things? Examples may be gradient of temperature, gradient of T, or more precisely, it can be, I can write in a 4-vector rotation as del mu of T. Pressure gradient, gradient of gravitational potential, gradient.
Sir,
All
I
these
have a
objects,
question.
yes,
We are talking about the covariant vectors and regarding the gradient being the covariant vector. What about the directional derivative?
yes, directional derivatives will come into this thing. We will come to that. We'll come to that.
Okay.
So I am trying to give you some, because somebody asked yesterday, I am trying to give you a very lucid definition. Of course, I am not going into those more details. Of course, there are more other examples. And in fact, when we go to general relativity, it will be more generalized. Okay, so this is in context of special theory of relativity. In the next slide, next page, I will go to general relativity and the ideas will generalize more. So because you asked this question, let me just give you one answer, is that so basically when we talk about covariant and contravariant vectors, the idea in both special relativity and general relativity is that the metric basically connects them, and vectors, they live in something called tangent space. Again, I mean, I'm probably going out of the context here, but since you asked, so sometimes it is denoted by this notation. For the covectors, they live in a completely different space, which is dual to this space, which is cotangent space, which is sometimes
Please, sir.
denoted by this. So this I did not want to go because essentially this will create a confusion. So I wanted to be a little bit more kind of a little bit less technical. So I just brush out these things in this discussion. Okay, but if you want, we can have a discussion later. Now, now the point is, every time we have this discussion on special relativity of special theory of relativity, we said that this is not the most general way of defining coordinate transformations. So in order to transit from this to general theory of relativity, the idea is to get rid of the idea of Lorentz transformation. That is the question that Einstein asked. Like, why should we be bothered about coordinate transformations which are linear in these x and t? Because essentially, if we have to, and why should we bother? Somebody asked yesterday also that why should we bother about inertial frame? Because defining inertial frame is extremely difficult. It's almost impossible because everything is being influenced by other particle. You cannot go to a completely otherwise isolated space and you define your uniform velocity with respect to which you are measuring something. It's not possible. It's not physically relevant. So, and also in daily life, on the surface of the Earth is an accelerating system. There are many examples where acceleration is going to take over your physics, and there this idea of inertial reference frame moving with uniform velocity is not going to work. However, what is going to not change is the form of the physical laws. They are not going to change if you change your coordinate system that can describe the physical laws. So essentially, you may need to go to some other frame, or some you may need to move with certain acceleration. Still, you need to write down the physical laws in particular reference frames which do not obey the laws of special relativity. That means the coordinates are not related linearly with each other and mixed with each other. So in such cases, you need a more general type of coordinate transformation, because Lorentz transformation is a very restrictive type of coordinate transformation, and it is applicable only to uniformly moving coordinates or inertial frame of reference. So we should claim a more general postulate: all laws of physics should remain covariant in any type of reference frame, not only inertial frame of reference. Okay. Now, as I said many times, even 2 minutes before, I was telling that the basic tool to study general theory of relativity is differential geometry, but because of shortage of time, we are just going to avoid that. We will focus only on some structures that differential geometry gives us, and the tensor calculus on a general manifold is that particular structure which we are going to discuss. Now, very briefly, how things are changing. Things are changing in the context of the way I have defined this line element ds square. Remember, this is an object which did not change if I go from one frame to another inertial reference frame. And the metric that I have defined, they were all having constant diagonal components, which are -1, +1, +1, and +1. Now I want to remove that constraint or restrictive definition. I want to make this metric itself function of space and time, and then want to see what happens. Okay. Now, for example, here I have defined in special theory of relativity the velocity 4 vector with respect to some proper time. Now, in GR, I will define it with respect to something which is known as an affine parameter. Okay. Here, I have defined some Lorentz, the covariant and contravariant vectors in this manner. And the components, the coefficients, these L mu prime nu, were constants when I was in the regime of special theory of relativity. But here in general theory of relativity, when I will define these objects will no longer, this coefficient particularly, will no longer remain a constant. So this is the basic generalization from using Lorentz transformation to general coordinate transformation. But to understand GR, we need to understand a little bit of tensor calculus. And we will consider the transformations of coordinates which are not Lorentz transformation. And we will also talk about tensors under general coordinate transformations, which need not be orthogonal and need not be linear. Okay. So let us actually go back even further and discuss a little bit about Cartesian vectors. All of you are familiar with Cartesian vectors. So I have a component, I have a vector which has components ai. And remember, when I define vectors, I just do not mean that the vectors have a direction and a magnitude. Rather, I want to define a vector in a way whose components behave properly under rotation. Why it is important? I hope all of you are familiar with the idea of a wave vector, right? All of you are familiar with the idea of a wave vector, which we generally call as 2 pi by lambda, right? Kx, ky, kz. Now, this object is a little bit complicated thing, because we all know about the wavelength of a vector, or wavelength of some quantity. Wavelength, we generally do not write it as a vector quantity. Still, we always write this wave vector as a vector. Why? Because the components of k, they transform properly under rotation, whereas if I want to write 1 by k to express my wavelength, they do not transform properly under rotation. So it is very crucial what type of any three numbers, if you take and put it inside a bracket and call it as a vector, it's not going to give you a vector. You have to have a certain transformation property. In case of vectors, it is the rotation, under which the transformation rules should be obeyed. So any three numbers is generally not going to give you a vector. So this idea, I mean the Cartesian vectors, I have written in terms of its components and the basis vectors. Now basis, you may all know that they need not be unique. You can write the same a vector in a completely different basis, which is denoted by ei prime, and accordingly the components of the vector will also change. But the vector remaining the same, I can equate these two equations, that ai prime should be ai ei vector. Now, if you take a scalar product of both sides of this equation with ej prime, another basis vector ej prime, then this object, because the unit vectors here are orthogonal, is going to give you delta ij, and on the other hand, ai will simply be written as ei dot ej prime. So I can immediately write from this left hand side that ai prime delta ij, this only gives you a non-zero component, non-zero number if I equal to j. So you just put the criteria that I equal to j, and then it becomes aj prime. The right hand side is this. I write this ei dot ej prime as lambda ij. So this is the relation between old and new components of the vector A. Now basis vectors are also related in this manner. Exactly in the same manner, you can say that the basis vectors are related. And also these quantities lambda ij, you can take them in this order and take their dot product, and it finally will give you delta jk, saying that this lambda ji is an orthogonal matrix. Now this a dot a, which is nothing but ai summed over, is unchanged under the transformation. So just like the scalar product, you can use this definition of ai prime and bi prime. This is exactly similar to Lorentz transformation, but in 3 dimensions. Okay. So instead of considering ai bj, you can now consider a quantity tij, which is a Cartesian tensor. You can define Cartesian tensor. One of the examples of Cartesian tensor is the moment of inertia tensor, which you may have already encountered. So this is something which will become your transformation property for the 3-dimensional Cartesian vector. Now come to the Minkowski space vectors. Just to remind you that this is something which we have already seen, but these objects L mu prime nu, there is one fundamental difference from those 3 vectors with these 4 vectors. These objects are not orthogonal in 4 dimensions. Rather, they satisfy something like this: L mu nu, eta mu rho, L rho sigma should be equal to eta nu sigma. Okay, so this is something which is what is known to us. Maybe Bhaswati can discuss this this identity in the tutorial. Now I want to give you some more ideas about coordinates in Euclidean space. It's basically the standard flat space which you are using more or less throughout all your life so far. So it is most often described using the Cartesian coordinates, but there is no hard and fast rule. There are other coordinates to describe Euclidean space, and one such coordinate is plane polar coordinate. Okay. So what is an Euclidean space? It is a set of points in n dimensions in which the scalar product is defined in this manner. X dot y between two vectors is x mu y mu, so that length of a vector you can define it as a square root of the dot product of x between x, which is nothing but x mu to the power half. And you can also find out what will be the angle between them. So this is the definition of the Euclidean space. So to express, so for example, as I said, that you can always write coordinates in an Euclidean space either using a Cartesian system or using a polar system like plane polar coordinate like r cos theta, r sin theta. And these x and y are related to r and theta. Similarly, r theta are also related to x and y. The inverse transformation exists. To express the components of a vector, exactly like this, which I just showed, in terms of the new coordinates, we may use this relation, which is our very known Lorentz transformation type of relation. But here we are talking about three space-time dimension. In fact, the example that I am going to give you is a 2D Cartesian to polar coordinate system transformation. Here, what I am doing is that my unprimed coordinate is the Cartesian system, and suppose that my primed coordinate is the plane polar coordinate system, that means denoted by r and theta. So you can always use these. Let me not confuse you. Let me use, instead of L, let me use lambda. Okay, because L always reminds you of the Lorentz transformation. But since we are not discussing anything with respect to time, let us denote it with lambda, which I have used for the Cartesian tensors. So that means we need to calculate these quantities, right? In order to find lambda in this particular problem, I need to figure out what are these quantities. So what values these mu and nu can take? They can take either 1 or 2. If mu is 1, then del x1 is nothing but x. I mean, x1 is nothing but x, and x2 is nothing but y in the unprimed system. And in the prime system, x1 is r and x2 is theta, right? So you can calculate these objects. Del x del r with theta constant is cosine theta. Del x del theta with r constant is minus r sine theta. Del y del r is with constant theta is sine theta, and del y del theta is r cos theta. Similarly, you can also calculate the inverse transformations. That means if you want to calculate del x prime, this is del x prime mu del x nu, and this is del x mu del x prime nu. So this is a set. Let me write here. This is a set where I am calculating the components of the metric del x mu del x prime nu, and here I am calculating del x prime mu del x nu, because my prime system is polar system. Now, so that once I have figured out all the components, so we can write the derivatives in the matrix form exactly in this manner, right? So dx alpha prime is del x alpha prime del x mu dx mu. So this is nothing but a column vector. This is a matrix, 2 cross 2 matrix, and this is another 2 cross 1 column vector. So dx alpha prime, what was my prime coordinate? My prime coordinate was r theta. So the first component is dr, second component is d theta. Similarly, this one is del r del x, this is del r del y, this is del theta del x, and this is del theta del y. Similarly, this is how del x dx dy will come. So you can clearly see how the calculation generalizes even in Cartesian system. Okay. So cos theta sin theta minus 1 by r sin theta plus 1 by r cos theta dx dy, and this is how the two coordinate systems are related to each other. Basis vectors, on the other hand, they transform in the opposite way. You can calculate it as a homework. You can try to calculate how the basis vectors transform. The basis vector transforms, let me also change the notation here. let me write it lambda, because L I have restricted for Lorentz transformation, but this is not exactly Lorentz transformation. So you can write this, you can calculate these objects, and you can write your basis vector as like this, because this is, so please correct this. I should not use L, I should have used lambda. I hope my goal is clear here. I wanted to write down the basis vectors in terms of these components. So the basis vector, as expected, the radial ER, the R basis, R hat basis vector is coming out to be a mixture of X and Y unit vectors. Similarly, the theta basis vector, theta vector is theta hat or E theta is coming out to be as a combination of EX and EY, but with different coefficients. These coefficients are figured out from this matrix, rather. So this is the relation between the, so you note one thing, for the coordinate differentials, this is a column vector. For the basis vectors, this is a row vector. Okay, so this is the difference between, they live in two different spaces. Okay, so the basis vectors that you are finding here, they are not normalized. That is one very important aspect. The basis vectors that you have found out in this relation and in this relation, you can clearly see that they are not normalized. But if you actually write down the known basis vectors to your polar coordinates in terms of the Cartesian basis vectors x hat and y hat, then this is their expression. How did I distinguish between them? For this, for my example, I have used a vector sign, and this is a hat sign on this ER and E theta, and clearly you can see that they are not, these vectors are not normalized, rather than these vectors which are normalized to unity. The ones that we have found have the feature ER dot ER equal to 1, but E theta dot E theta equal to R square. So sometimes you will hear the terminologies, and this is just to remind you of the terminologies. These basis vectors with this vector sign, which I have shown in this example, they are sometimes known as coordinate basis. They need not have the normalized basis vectors, and these are non-coordinate basis vectors. They are represented in the discussion with the hat sign. Okay, so now you consider a function which is given by f as a function of x mu, which assumes a number to any space-time point x mu. Now you consider a path through this point x mu, and this path is parameterized by lambda. Okay, and lambda may be a number between 0 to 1. We all are familiar with how to parameterize a curve. I told you yesterday. So you can always parameterize a curve with a parameter lambda, and this parameter can take values 0 to 1, just like theta can take values between 0 to 2 pi when you use theta to parameterize a circle. Similarly, this lambda also can take values between 0 to 1. Then this f x mu is a function of lambda. It represents a function of that path parameter, giving the value that f takes for every space-time point along the path. How does, then you ask this question, how does this f change with lambda? How does f change with lambda? It's very easy to find out. You write df d lambda, that means dx mu d lambda, del f del x mu. So this is true for any function of f, and so we could write this dd lambda, this object dd lambda, as dx mu d lambda del del x mu, and it exactly looks something like x vector being written as x mu e mu basis vector, with this object dx mu d lambda playing the role of the components of the vector, and as if this del del x mu as the basis vector. Okay, so in our example of polar coordinates, er is del del r and e theta is del del theta. So this is one example where I just wanted to give you some hint that these objects, these differentials, these derivatives and the differentials can also act as basis vectors. Okay. So now I come to the general definition of vectors and tensors in a general manifold. So this is something which all of you are familiar with, contravariant vector, but unlike L nu mu or L nu prime mu, this object essentially, sorry, this object essentially is no longer constant, rather it can be a function of space-time. Similarly, covariant vectors, the transformation law for covariant vector is given by this. This object, unlike M nu prime mu, is now no longer constant. So you can generalize this whole thing to higher rank objects. Instead of constants sitting there, you will now have coefficients which are dependent on space-time. And exactly similar way, you can define higher tensors, higher rank tensors with different indices. Say for example, A mu, C nu. I can call this whole object as a tensor with rank 2. So I will denote this object with a notation, say T mu nu. That's what I have shown here. Similarly, you can define the covariant object, which is B mu D nu, which can be S mu nu with a lower symbol. And you can also define the mixed object, which is like this. So I request every one of you actually to write down the transformation properties at least once by hand, such that you know where to put which index and where to put the prime, because this is very, very crucial. This is the whole crux of the course, that you know how to manipulate with tensors. Okay. Similarly, the contraction is defined exactly in the similar manner that we have defined during the definition of the special theory of relativity tensors, the 4 tensors, 4 vectors. So this is exactly take this q mu nu and replace this nu with mu, similar index. And you can see immediately by writing the transformation property why this summation actually removes one index extra. So for example, write down the transformation property of q prime mu mu. The first term will be del x prime mu del x rho. Second term will be del x sigma del x prime mu. Why mu? Because mu has to be matched there. There will be no index mismatch between in a tensor equation between your left hand side and the right hand side. Whenever you are writing the indices on the left hand side, the exact similar free index should match the right hand side free index. So that is the only criteria here. So you write this as the q rho sigma, but you note that this is nothing but this using the chain rule. You can actually just remove this mu index. So what remains is del x sigma del x rho q rho sigma. But I know what is del x sigma del x rho. Del x sigma del x rho is nothing but Kronecker delta sigma. And as sigma and rho, these indices match, then Kronecker delta is 1, otherwise it is 0 always. So rho and sigma must be same. So I change rho with sigma. And since rho is summed over or rho is repeated, I can call this as a dummy index and I can write it as q mu mu. So that is the way contraction works. The object does not change under a coordinate transformation. That means I am talking about a tensor of rank 0, which is a scalar. Now, contraction is the procedure to reduce the rank of a tensor. Okay. Again, I am actually keeping this very important theorem, quotient theorem, to be discussed in the tutorial, because I do not want to spend time on this thing. Now, let me also give you the rules of raising and lowering indices in a general manifold. So this is in special theory of relativity, we have seen how you will raise and lower your indices with the help of the tensor, which is Minkowski space tensor, which is eta mu nu. But in GR or in any general manifold, the whole thing generalizes to or replaced by eta mu nu is being replaced by g mu nu. This is known as the metric tensor. Metric tensor itself is a covariant tensor of rank 2, And so you can write down the transformation law for the metric tensor as follows, that you have two indices to correct, and you therefore will have two coefficients in front of the corrected metric. So you will have one coefficient which is del x prime mu del x rho, and another coefficient will be del x sigma del x prime mu g rho sigma. Remember, these rho sigma and rho sigma, they are basically contracted, and here mu and nu are free indices, here mu and nu are also free indices. So I am stressing this many times because this is what you are required to be familiar with. Similarly, if you want to write down the transformation law with the upper components of the metric, then this is the transformation law. Now, you may ask, we can I mean, how can we find this relation from this relation? So that can be figured out from this ds square g mu nu dx nu, and I know how this transforms. So g mu nu, I will write it as del x mu del x prime rho. I will write this as del x nu del x prime sigma, and I will keep this dx prime rho dx prime sigma terms here, such that this appears like a ds square in a new coordinate system. Of course, it appears like a ds square because this object is nothing but your g prime rho sigma, and this is nothing but dx prime rho dx sigma. So this thing remains invariant, ds square remains invariant even under a general coordinate transformation. Okay, so this is what I wanted to tell you regarding the metric tensor part. And in general, raising and lowering works exactly in the similar manner that we have utilized during our discussion of 4 vectors and tensors. Only difference is that the Minkowski metric is being now replaced by all these general metric tensor. So for example, let me write it down. Let me give you one example. This is say one example which I wanted to show you. So t prime mu nu. First, I will raise this index g prime nu alpha, t prime mu alpha. So the index that I wanted to raise is this one, nu. So I will keep this nu here, and I will bring another index alpha, such that this alpha is contracted, okay, and mu remains unchanged, unaffected. Now I know how g prime nu alpha transforms in terms of my metric tensor in the old coordinate system, and this is the transformation rule: del x rho, del x prime nu, del x sigma, del x prime alpha, g rho sigma. And I also know how a contravariant rank 2 tensor transforms, and that is del x prime mu, del x beta, del x prime alpha, del x tau, t beta tau. So you take all these coefficients with you, and you note particularly this term and this term. There is this del x prime alpha in the numerator and del x prime alpha in the denominator. So I will simply have del x sigma del x tau from these two terms, which is nothing but delta sigma tau, which I have written here. So this, with the help of this Kronecker delta, will become this expression, and you will write down the transformation property of the mixed tensor in this following manner. So essentially, you know that if there is a primed here, that means this prime is on mu and nu also. So this index needs to be corrected. This is corrected here. This also needs to be corrected. This is corrected here. For this contravariant, I have this component, this coefficient, and to correct the covariant component, I have this coefficient. Now I come to a very important topic, which is the derivative of tensors. Now, suppose mu is not only defined at a point, rather this object mu is a field. It is a function of x nu. Okay. So you should ask the question that what is this del mu del x nu? How does mu change as I move in my space time? Of course, when I ask, as I said, that when it is asked how a particular quantity change, immediately write down the primed coordinate system. So del A prime mu, del X prime mu. I want to first write down the A prime mu transformation law. A prime mu transformation law is written here. So this is del X prime mu, del X rho, A rho. What about this term? I will write it like this. I will write del X prime nu as del X sigma del X prime nu, del X sigma A rho. And this will have del X prime mu del X sigma. This will operate first on this, and then this del X prime nu will operate on this object. Earlier, when we were discussing Lorentz transformation, this object was a constant. So it does not matter. It directly acted on this. But now I also need to take care of the derivative of this object. So I will have a term like del X sigma del X prime nu, del 2 X prime mu, del X sigma, del X rho, A rho. Okay. So this is something, if you look very carefully, that I have a term which is del X prime mu, del X rho. This is this term, del X prime mu, del X rho, del X sigma, del X prime nu, then del A rho, del X sigma. Had there been only this term, then I could have said that my derivative of a tensor transforms exactly like the transformation rule of a mixed tensor, which I have shown here. But I have a second term. This second term is causing all the problem. Had it been Lorentz transformation instead of general coordinate transformation, this term would have become 0, because there is a second derivative of the primed coordinate, and second derivative of the primed coordinate is always going to be 0, because these prime coordinates in special theory of relativity are related via primed and unprimed coordinates are related via the Lorentz transformation. Lorentz transformation itself is linear in X and T. So this would have vanished. But in general coordinate transform, it will not vanish. So if we ignore this term, del A mu, del X mu transform exactly like a mixed tensor, but we cannot ignore when we are talking about general coordinate transformation. So the derivative of a tensor, it is a very crucial conclusion. Derivative of a tensor does not transform as a mixed tensor in general. Okay. Now you may ask, why del A mu, del X mu does not transform like a mixed tensor? It's a valid question. I have two quantities which are tensorial objects, but essentially when I am taking the derivative, this derivative is not behaving like a tensor. Remember, transformation rule is a local definition, whereas partial derivative of a vector field is generally given by this formula, which all of you are familiar with, where you have a vector evaluated at some point and another vector which is evaluated at near very infinitesimally close point, and then you divide it by that distance, this infinitesimal distance, and take the limit delta x nu prime going to 0. Now this right hand side in this expression is the difference between two vectors which are evaluated at two different points on the manifold. Now transformation for these vectors at two different points, they generally look something like this. If you write down the vector at a point x prime plus delta x prime, there will definitely be a coefficient exactly like this, exactly like this in front of this object, and then there will be a nu x plus delta x. Similarly, for a prime mu x prime, there will be another coefficient which is the derivative between the primed and unprimed system, and a nu evaluated at x. So these objects, these transformation matrices, they are evaluated at two different points. Transformation matrices are evaluated at two different points in the manifold. When we took difference, the resultant quantity does not transform as a tensor. This is very crucial because transformation rule is a local definition, but partial derivative definition requires the vectors to be evaluated at two nearby points. And what it says is that the transformation rule is not followed simply because the vectors had to be evaluated at two nearby points. So T prime x prime plus delta x prime and T prime x prime are elements of two different tangent spaces. They are elements, these objects, not T. Let me not write T. I should write it A. The vector that we have evaluated, they are basically taken from two different spaces. And that is why the derivative of a tensor or vector does not transform properly. Let us understand this point from the perspective of an example. Let us take 2 points on a unit circle. Again, I give you another example such that this will be visualized clearly. And suppose on this circle, I am taking 2 points. One is P, another is Q. P, the coordinate of P in Cartesian system is 1, 0. That means it is on the x-axis. And the coordinate of Q is 0, 1. That is, it means it is on the y-axis. And now you take a vector V whose components are 1 and 0. That means it is basically, and this vector is situated at P. So that means this vector V is a unit vector in Cartesian coordinate pointing in the x hat direction, right? So you are taking a vector V, which is same as saying that it is 1 x hat. This vector is 1 x hat plus 0 y hat. That is what I have written here. Now, in the Cartesian system, V is given by x hat 1, 0. Now I transport the vector V from P to Q without rotating it and without changing its length. Since in Cartesian system, x hat and y hat are always horizontal and vertical respectively, that is, they are same at all points on the entire plane, the vector V still points in the x hat direction when I have moved it to Q. Okay? Is it clear to all of you? This is very crucial because I am going to introduce the idea of parallel transport now. So when I move the vector unit vector V from the point 1, 0 along this circle to the point Q at 0, 1, because the unit vector in Cartesian system always remains in the x hat direction, the vector does not change when I move from point P to point Q in Cartesian coordinate system. So at Q, this is the same vector. Now let us look at the same problem, what happens in polar coordinate. Polar coordinate, one of the uniqueness of polar coordinate is that the unit vectors are no longer fixed. Rather, their r is always radially outward and theta hat is always radially always increasing in the direction of increasing theta. That means r hat is always radially outward and theta hat is in this direction, where theta is increasing along this direction. So I have shown on this circle, different concentric circles, the directions of r hat and theta hat. I also know how x and y are related to r and theta. And I also know how the unit vector is defined. If you have forgotten, just go back to the book by Speisel. This is the definition of the unit vectors. R hat is defined as del r. This is the r vector divided by mod of del r vector del r. What is r vector? R vector is nothing but r cos theta x hat plus r sin theta y hat. So if you evaluate this will give you cos theta sin theta, and theta hat, if you evaluate that, it will give you minus sin theta cos theta. So this is all in terms of x hat and y hat coordinates. So r hat and theta hat are already known. Therefore, I can write what is the value at P. P means if I am at P, let us look at this figure. P means theta is equal to 0, and if we are at Q, then theta is equal to pi by 2 from this figure. So theta equal to 0 means what is r hat? From this expression, r hat is 1, 0, theta hat is 0, 1. Similarly, at pi by 2, that means at Q, r hat is 0, 1 and theta hat is minus 1, 0. Therefore, you can see immediately that at P and Q, the unit vectors are completely changed. So in polar coordinate, I may write my vector V, which is 1, 0 in Cartesian system. We want to write V in polar basis. How can I write that? I can write that just by mentioning this, that at P, I know that P has the coordinate x equal to 1, y equal to 0. At the same time, I know theta is equal to 0. Therefore, my vector is 1 r hat plus 0 theta hat. So Vr is 1 and V theta is 0. So the radial component of the vector in polar coordinate is 1 unit and the theta component is 0. Now, what about the point q01 where theta is pi by 2? What is the form of this vector v1 comma 0? I do not know what will be the form. I need to find out. Suppose my radial coordinate is v0, and at that, suppose my radial component is vr, and I need to write it here as r hat. R hat at theta pi by 2 is given by 0, 1. So I have put 0, 1. Similarly, the theta component is v theta, and theta hat is minus 1, 0 at point Q. So this is my expression of the vector. And if you compare the coefficients on both sides, you can clearly see Vr is 0 and V theta equal to 1. Therefore, V at Q in polar coordinate is 0, comma minus 1. So I have a vector which, when I have transported from one point P, that point the vector was 1, comma 0. Now it has changed to a vector 0, comma 1 at point Q. So Cartesian basis does not rotate. So parallel transport of vectors look trivial. Polar basis changes the position. So even in flat space, the components of a parallel transported vector changes. This is very, very crucial. So I have tried to keep the vector direction same, and I have tried to move the vector along the circle. So I have kind of tried to move the vector parallel by keeping it parallel to itself. But in the process, I saw that Cartesian system, even though it did not hurt me, but while transforming from one point to another, by always trying to keep the vector parallel, it still did not remain parallel in polar coordinate system. So this leads us to the problem of parallel transport of a vector in general relativity, or in general in differential geometry. We considered two infinitesimally close points, x alpha and x alpha plus dx alpha, a scalar function f and its difference at two different points, which is f evaluated at x alpha plus dx alpha, and f evaluated at x alpha. If I take their difference, it still remains a scalar. But I have just now seen that we cannot do this for vectors, because if we want to do this for vectors, I have just now seen that the derivative of a vector does not remain a vector or 4 vector or tensor under a coordinate transformation. So the question is, how do we find the differential of a vector? Because the vectors are not same at two nearby points. You can think of it in terms of moving on the surface of the earth. Suppose you want to move from some place on the earth to a very further away place by always keeping a vector with you. But as you move along, the vector's direction is going to change. So when you go to a different point on the curved surface, the vector's direction is definitely going to change. So the point is, whether should I be able to call it the same vector or not? The best way to answer this is that we parallel transport the vector from x alpha to the point x alpha plus dx alpha, and after having parallel transported, we take the differential such that we can claim that the vector always remain the same. Now it is a valid procedure because adding and subtracting the vector occurs at the same point. Okay, so I will define the differential of a vector, which is v mu x alpha plus dx alpha minus v mu evaluated at x, and this I will add some extra bit which I denote by delta v mu x. So what is this delta v mu x? Delta v mu x is the quantity which after parallel transport we have gotten as an extra piece on top of v mu x. So this arises. Why does this delta v mu arise? This delta v mu arise because of the parallel transport that I have done. So we want to know how much the components change when the vector is parallel transported from one point to another very close point, on which, so then we should ask the question, on which does this extra piece delta v mu x depend? Well, of course, it is going to depend on by how much it has been moved. That means dx alpha. So delta v mu should be proportional to dx alpha. That is, it is proportional to the displacement by which the vector has been moved. Similarly, it should also remain proportional to the original vector, because if the vector is small, then the change should be small. If the vector is large, the change should be large. So therefore, on these two objects will the quantity delta v mu depend. So I will write it as delta v mu equal to v beta dx alpha, and I will incorporate a quantity here which is gamma, but now it has three indices, one index to take care of this beta, another index to take care of this alpha, and also to take care of this free index gamma, and it is introduced as a constant of proportionality, and the negative sign is just a convention. Okay. So this object which I have just introduced is sometimes called Christoffel symbol, or sometimes called the connection coefficient, sometimes called the affine connection. So there are many names to it. We don't know the form of this object yet. What we know is that it has arisen because as a constant of proportionality, and because of parallel transport, there will be an extra piece that is added to this, such that I get a vector at the same point, and such that I can evaluate, I can apply my transformation rule in a proper way. And because I have seen that vectors evaluated at two different points does not give me the proper transformation law of tensors. So how should I get the expression of gamma mu alpha beta? That will come naturally. I will discuss that in the due course of time, but let us now look at our basic definition. So this is the definition with which we started, that it is basically the difference between two vectors evaluated plus some added quantity which I call delta v mu, and this delta v mu is now of this form. So I have v mu x alpha plus dx alpha minus v mu x alpha, and then plus gamma mu beta alpha v beta dx alpha. So I have del, but now if you look at this object very carefully, this is something which is the normal partial derivative, right? I can write it as del v mu del x alpha dx alpha. And then I have this object. So I will write this whole thing by taking dx alpha common in this manner. So just like dv mu is related with the partial derivative in this manner, the infinitesimal element dv mu, we call capital dv mu as the covariant derivative. Okay, so this capital dv mu is basically nothing but this object, which is multiplied by x dx alpha. So this whole thing, this whole object, let me put it in a different this thing. This object is what we call the covariant derivative of the vector v mu with respect to the coordinate x alpha. Okay, sometimes it is denoted by in this manner also. Covariant derivative is denoted by a semicolon, and the normal partial derivative, it is denoted by a comma. Okay, so this is the notation that we are going to use, or we may also use this notation where the covariant derivative is expressed as gradient, this symbol del alpha v mu. So what we have done here is this. I have defined this quantity, which is a covariant derivative of a vector field. Now this covariant derivative, we have seen, contains some partial derivative of the vector and some extra term, which is this. Why this extra term arisen? This has arisen because this term del v mu del x alpha does not obey the general coordinate transformation property. It does not behave or does not transform as a mixed tensor. This is introduced such that the whole expression transform like a tensor. So that means this whole expression v mu semicolon alpha is now a tensor. So how should we do the same for the covariant derivative? Of course, this is very easy to do. I can define the covariant derivative, the covariant vectors covariant derivative in the following manner. I will take this v mu u mu, it's a scalar product, and I know that if I apply this capital D on this object v mu u mu, this is going to be same as d of v mu u mu, because v mu u mu is a scalar. It does not matter, it does not change under coordinate transformation. So I can call this as simply d of v mu u mu. And then I will use the definition of d v mu, that means the covariant derivative here, and this is what we are going to find out. We are going to find out the rule for covariant derivative of a covariant vector. So this is basically the right hand side is very easy. Right hand side is just a normal partial derivative, and this object we know, we just have figured out that this is this object, and what we want to find out is d u mu with a lower object. So if you do this calculation, please go through this calculation. I will share this calculation, and I will also request Bhaswati to do the same calculation in the tutorial. This is the covariant derivative of a covariant vector. So the covariant derivative has this particular form, del alpha u mu. Remember, we have del u mu del x alpha, which is the standard partial derivative, and this object is the correction term. Now, which coefficient or which index am I going to correct here? The index that I am going to correct here, let us look at the contravariant expression first. The index that I am going to correct here is this mu. Okay, so mu is being changed to beta. So how should I write down? Given a suppose I give you any arbitrary vector, say del a rho, sorry, not del a rho. Suppose I want to find out what is the covariant derivative of a rho with respect to x beta. So how should I write down the final expression? Of course, the covariant derivatives indices remain unchanged, a rho comma beta, plus I know that there will be this gamma term, correction term, and then I know that there will be a term also. I definitely know that this index cannot be there because this is the index that needs to be corrected. You see, it is here, it is mu, here I have changed it to something else. So let us call it lambda, some different lambda. That lambda should come here. But this rho index should be there, otherwise I will have terms which are different than different indices in the left hand side and right hand side. And I also have a beta which is free here, and this beta is no longer here in this right hand side second term. So I will put this beta here. So this is how we write down the general rule, the general covariant derivative of a contravariant vector. Okay, I hope that it is clear to you, because I think my time is over. I have just introduced the two different types of covariant derivatives in this class. Tomorrow, I thought of actually finishing all these things, but probably Bhaswati, if you are here, probably you will be able to introduce these covariant derivatives of second rank tensor in the tutorial also. And then we will see what is this object tomorrow, what is this Christoffel symbol object tomorrow in more detail. Okay, so let me now stop here, and if there are any queries, any questions, comments, you can please ask.
Thank you, sir.
Let me see if there
Now
are
20 questions.
and, okay, difference between tensors and vectors. Okay, difference between covariant and contra. I thought I already told about contravariant and covariant vectors. Physical significance. Oh, I thought I defined the physical significance. Oh, achak. No. There is nothing called contravariant derivatives. Covariant derivatives is something which I have defined. So let me go back to my notes and show it again. Sorry, this one. So someone asked the physical significance of covariant and contravariant vectors. I thought I already told you. Let me go back to that slide again. Here. So in principle, suppose I have a vector. Any vector I can define either with an index up or an index down. Physically, these two quantities are different. Why they are different? Simply because they follow different transformation properties. So what is the transformation property of a mu prime? So this is nothing but del x mu prime, del x nu, a nu. And this one, its transformation property is different. A mu prime is del x nu, del x did I do? Del x mu prime a nu. Now these two quantities are completely different. In the context of Lorentz transformation in special theory of relativity, this is something which is L mu prime nu, and this is something which is M nu mu prime. And these L mu prime nu and M nu mu prime are two different matrices which are orthogonal, which are not orthogonal to each other, but rather, which are orthogonal to each other. So because, let me write it. L, let me be a little bit careful. Mu prime nu, M nu, let me write M sigma mu prime is delta sigma nu. So this is mathematically what it is. And as I said, contravariant vectors, they are basically representing an actual direction. Suppose you are on the surface of the earth. What happens when you are on the surface of the earth is something which is very crucial for us to understand. There are two kinds of quantities you can describe by standing on the surface of the earth. Objects that represent actual directions or displacements. Suppose you are walking in the east direction or in the south direction or in the north direction. So these are objects that represent actual directions. So these are vectors. Contravariant vectors are vectors which represent some objects which has specific direction, say displacement, say velocity, say momentum, say current. All these are such objects. Covariant objects, covariant vectors, on the other hand, they are something where you put some vector and it's like a slot machine. You insert some vector, and as the process, some other object acts on this vector, gives you a scalar. So this object turns out to be a covariant vector, and that is what I mentioned when I said that. Where did it go? This one. When I said that I asked the question, how del phi del x mu transform? So that means I need to write how del phi prime del x mu prime be written. So del phi prime del x mu prime is nothing but del x nu del x prime mu del phi del x. And this object, importantly, is this M mu nu mu prime. And this object is basically the 4 vector that I am talking about, and this is a covariant vector. So this is this object is nothing but some gradient operator. So gradient of temperature, gradient of gravitational potential. So this is the operator acting on a scalar quantity, giving you something. So this is basically not representing any actual direction. Okay, so this is the difference between covariant and contravariant objects. Now, what was the second question? Physical significance and of covariant derivatives. Okay, there is nothing called contravariant derivatives. There is only covariant derivative that I have defined. Now, why did I define covariant derivatives? Because in general space-time coordinates and in general, when we consider the general coordinate transformation, not Lorentz transformation, we have seen that the derivative of a 4 vector or derivative of a tensor do not behave properly under a coordinate transformation. When I say, what do I mean by do not behave properly under coordinate transformation? That means that I cannot write down the let me write it here again, sorry. I cannot write down del v mu del x alpha with respect to these two coefficients will be there, which I have denoted. So for example, it will be del x prime mu, del x rho, del x sigma, del x prime alpha. Okay. So had it been like this, I could have said that this object, sorry, del v, sorry, I think I wrongly wrote it. Del v rho, del v rho, del x sigma. Had it been, had I been able to write this in this form, I should have simply say that it is a mixed tensor of rank 2. One contravariant rank, one covariant rank. But it is not. I have just seen that it also has some terms which is basically double derivative term. This term under general coordinate transformation does not go to 0. Lorentz transformation, if we had considered, it would have been 0. But for general coordinate transformation, there is no guarantee that this will be 0. And therefore, the tensor transformation properties are not being obeyed because of the presence of this inhomogeneous term. And that is why when I am working with vectors or tensors in a general space-time manifold, I am not able to define a derivative which remains covariant under general coordinate transformation. And why do I need these covariance? Because physical laws, according to Einstein, should not change if I go from one coordinate frame to another coordinate frame. I do not necessarily need inertial reference frame. Any reference frame from one to another, if I move, the physical laws should not change. Physical laws should not change their form. That is what is generally meant by covariance. So this will change the whole game if I have a second derivative term sitting in this transformation property. And that is why I said that I introduced the idea of parallel transport. And by introducing the idea of the parallel transport, I was able to introduce an extra factor in that expression of d, v mu. So let me go to that page where I introduce this. I think it is here. So when I introduce this, I introduce just by saying that after parallel transport, we have an extra piece, and this extra piece is on top of this v mu x. And this arises simply because of parallel transport, because I have tried to move the vector always by keeping it always parallel to itself, because parallel vectors, I can just put it, I can just take it back to this point and do subtraction, addition, whatever, because when we need to do subtraction, addition, even apply the transformation properties, I need the vectors to be at the same point. But physically, the vector has changed from here to here. So when I just try to keep these two vectors parallel, this vector and this vector are not same. Some change has been introduced because of that. So that change is incorporated in this. And this incorporation actually gives me a quantity which I have just now seen is dv mu, which is basically nothing but a covariant derivative. And this covariant derivative will obey all the properties of tensor transformation laws. Okay, yeah, I think that's it. Any other comments, questions? It's okay. If not, I think let us conclude this session now.
Thank you, sir.
Okay, thank you.
So now we'll be having a lunch break from 1:25 till 2:30, and we'll be resuming the tutorials from 2:30 onwards. So let us meet again at 2:30. Thank you.